Have you ever wondered how we can predict the path of light through complex optical systems? How lenses focus light to create images, or how telescopes can see distant stars? The answer lies in the powerful technique of ray tracing. Today, we will explore how matrices can simplify this process. Ray tracing is essential in optics because it allows us to predict the behavior of light when passed through lenses, mirrors, and other components. It also allows us to design and optimize optical systems like camera, microscope, telescopes, and etc. Ray tracing allows us to analyze and troubleshoot existing systems. And finally, ray tracing allows us to visualize complex optical phenomena. To simplify our discussion, we suppose that the optical rays transfer in the same plane. So the problem is basically two-dimensional and is applicable to systems with planar geometry. However, if you understand it well, it won't be difficult to generalize the problem to three dimensions. In addition, we assume that the angle of ray with respect to the optical axis is very small, so that the paraxial approximation is valid. In the next slide, I will show you that we can describe a ray by its position and angle with respect to the optical axis. As we will see, the output position and angles are related to the input ones by linear algebraic equations. Therefore, we can describe the optical system by a 2 by 2 matrix called transfer matrix. We consider rate transfer in the YZ plane of a circular symmetric system whose optical axis is along the z direction. We said circularly symmetric because nothing is special about the YZ plane. So, if you consider every plane perpendicular to the optical axis, the same argument holds. As we said earlier, at each z, the ray is characterized by an angle theta with respect to the z-axis, and also the coordinate y of its crossing point. Our problem is this. Given y1 and theta1 at plane z1, which is called the input plane, we want to find y2 and theta2 at plane z2, which is called output plane. In the paraxial approximation, we can write sine of theta is almost equal to theta. And you should remember from calculus that the slope of a line is given by tangent of theta, which is approximately equal to theta for small angles. So in general, we expect that the following relation holds between the output and input variables. y2 equals to a constant a times y1 plus b theta 1, and theta 2 equals cy1 plus d theta 1. We can write this in a matrix form called transfer matrix. The first row of transfer matrix M is A and B, and the second row is C and D, as you see in the equation. In the following slides, we will find the transfer matrices of some simple optical systems. The simplest case is free space propagation. As you see in the figure, the angle theta does not change with the propagation of the ray, but position changes. The slope of the line in the figure is theta 1, which doesn't change. This means that theta 1 equals to theta 2. And we remember the well-known equation y equals ax plus b from calculus. Here, the horizontal displacement is d, as you see in the figure, and the y-intercept is y1. So we can write theta 1 equals to theta 2 and y2 equals y1 plus theta 1 d. Therefore, the transfer matrix for this system is 1d in the first row and 0, 1 in the second row. Next, we consider the refraction at a planar boundary. At the boundary, the ray is not transferred, only its angle has changed, as you see in the figure. So I can write y1 equals to y2, and according to the Snell's law, I can write n1 theta 1 is almost equal to and 2 theta 2 for small angles, and refractive indices N1 and N2. So the transfer matrix for this system is 1, 0 in the first row and 0 and N1 over N2 in the second row. The next example is refraction at the spherical boundary. Look at the figure. In the previous videos, we showed that y1 is approximately equal to y2, and theta 2 is approximately equal to n1 over n2 times theta 1 minus n2 minus n1 over n2 times y over r. Here, r is the radius of curvature, which is positive for a convex boundary and negative for a concave boundary. So the transfer matrix for this system is 1, 0 in the first row and minus n2 minus n1 over n2r and n1 over n2 in the second row. The next example is ray transmission through a thin lens. Since the lens is thin, the position y basically doesn't change. So I can write y1 equals to y2. But here we have two surfaces, one convex in the left side and one concave in the right. So we must multiply two matrices for two spherical surfaces. This remains an exercise for you to show that theta 2 equals to theta 1 minus y over f, where f is the focal length of the lens. So the transfer matrix for this system is 1, 0 in the first row and minus 1 over f and 1 in the second row. In the last example, we have considered the reflection of a ray from planar and spherical mirrors. For a planar mirror, the position has not changed after reflection, and the reflection angle equals the incident angle. So I can write m equals to 1, 0 in the first row and 0, 1 in the second row. Now the spherical mirrors. Here I show it with more details. The ray starts at point P1 at angle theta 1, as you see in the figure. After reflection from the mirror, it meets the optical axis at point P2, but the angle is now minus theta 2. Now theta 0 in the figure is an external angle for the left triangle. Therefore, I can write theta 0 equals to theta plus theta 1. Also, angle minus theta 2 is an external angle for the second triangle. Therefore, I can write minus theta 2 equals theta 0 plus theta. If we add these two equations, we get minus theta 2 plus theta 1 equals 2 theta 0. Since theta 0 is very small, I can write theta 0 is approximately equal to tangent of theta 0, which is y over minus r. Therefore, I can write minus theta 2 plus theta 1 is approximately equal to 2y over minus r. I didn't write the details because I have discussed this problem in my previous videos. Now we have the relation between theta 2 and theta 1. And also we know that in the reflection point, y2 equals to y1. For simplicity, we call it y. Therefore, the transfer matrix for this system is 1, 0 in the first row and 2 over r and 1 in the second row. I recommend you to do this last example by yourself and prove that m is equal to 1, 0 and 2 over r and 1.